Morning broke quietly across the towering slopes of Mount Rainier, yet instruments watching the volcano were already recording something unusual. Far from the dramatic explosions that many people imagine when they hear the word volcano, another kind of danger had emerged from one of the mountain's ancient glaciers. Scientists at the United States Geological Survey's Cascades Volcano Observatory confirmed that an outburst flood originating near the South Tahoma Glacier triggered a debris flow that raced through Tahoma Creek on the 3rd day of July, 2026. The announcement quickly attracted attention because Mount Rainier remains one of the most closely monitored volcanoes in North America, not simply because of its volcanic history, but because of the immense volumes of ice covering its summit and upper slopes. While the event itself remained relatively small and contained, it served as another reminder that one of the mountain's greatest threats does not require lava, ash clouds, or a volcanic eruption. Mount Rainier rises approximately 14,411 feet, or about 4,392 meters above sea level, making it the tallest volcano in the Cascade Range. Visible from hundreds of miles away during clear weather, its snow-covered summit dominates the landscape of western Washington. Millions admire its beauty every year, yet scientists have long regarded it as one of the most hazardous volcanoes in the United States. That assessment is based less on the likelihood of an imminent eruption than on the tremendous amount of ice, snow, loose volcanic rock, and unstable slopes that cloak the mountain. Unlike volcanoes that produce frequent lava flows, Mount Rainier carries another hazard capable of reaching communities many miles away with little warning. Massive mixtures of water, volcanic sediment, boulders, trees, and glacier ice can rush down river valleys at highway speeds. These destructive flows are known as lahars, and Mount Rainier possesses all the ingredients necessary to produce them. Many people assume such flows require an eruption, yet history has repeatedly shown that they can begin without magma ever reaching the surface. The latest event illustrates precisely that point. According to the United States Geological Survey, seismic monitoring stations detected vibrations consistent with a debris flow moving through Tahoma Creek during the early hours of the 3rd day of July. Careful review of seismic signatures, field observations, weather conditions, and satellite information led scientists to conclude that the event originated from a glacial outburst flood rather than a landslide. That distinction matters because it reveals the mechanism responsible for mobilizing enormous quantities of sediment already resting along the valley. Glacial outburst floods occur when water stored within, beneath, or alongside a glacier is suddenly released. Instead of gradually draining over days or weeks, enormous volumes of water escape in a relatively short period. Once unleashed, that torrent can rapidly erode loose rock and volcanic sediment, transforming a surge of meltwater into a debris flow capable of carrying boulders larger than automobiles. Scientists specifically classified the event as a debris flow triggered by an outburst flood from the South Tahoma Glacier. Importantly, they emphasized that evidence suggested the debris flow likely remained confined within Tahoma Creek and probably did not reach the Nisqually River. That finding indicates a relatively limited event, consistent with many previous episodes documented at the glacier over several decades. For residents familiar with Mount Rainier's behavior, the announcement sounded remarkably familiar. The South Tahoma Glacier has developed a long history of generating debris flows without volcanic activity. Records extending back to the late 1960s reveal repeated events originating from this glacier. Since approximately 1967, numerous debris flows have traveled down Tahoma Creek after sudden releases of glacier water destabilized loose sediment accumulated along the drainage. This recurring behavior reflects the unique geology of Mount Rainier itself. Unlike solid granite mountains, Mount Rainier consists largely of layered volcanic deposits accumulated over hundreds of thousands of years. Successive eruptions built thick sequences of lava, volcanic ash, fragmented rock, and hydrothermally altered material. Many of these deposits remain surprisingly weak. Water flowing across steep volcanic slopes easily erodes them, especially when sudden floods provide extraordinary energy. The mountain's glaciers further complicate matters. Mount Rainier supports more glacier ice than any other peak in the contiguous United States. More than 24 named glaciers descend from its summit, storing enormous quantities of frozen water. During warm weather, seasonal melting contributes steadily to streams. Occasionally, however, meltwater becomes trapped within cavities beneath glacier ice or behind temporary ice dams. As pressure builds, the ice barrier eventually fails. Once failure begins, the release often accelerates dramatically. Water escaping beneath the glacier acts like a powerful hydraulic tool. It scours sediment from valley floors, undercuts stream banks, and entrains volcanic material lying in its path. The resulting mixture rapidly thickens until it resembles flowing concrete more than ordinary river water. Observers frequently describe debris flows as moving walls of mud filled with trees, logs, rocks, and shattered ice. Their density allows them to transport enormous boulders while destroying bridges, roads, and forests with remarkable efficiency. Although the recent event remained relatively modest, it perfectly demonstrated that this process remains active today. Some social media discussions initially suggested a landslide had occurred. The United States Geological Survey clarified that interpretation. Available evidence indicated the debris flow originated from a glacial outburst flood rather than a dry slope failure. While both processes can produce similar downstream effects, understanding the trigger helps scientists refine hazard assessments and better anticipate future events. Dry landslides generally begin when unstable rock masses collapse under gravity, often following heavy rainfall, earthquakes, or progressive weakening of slopes. Outburst floods, by contrast, begin with sudden releases of stored water. Although either mechanism may eventually mobilize sediment into debris flows, identifying the source provides valuable insight into glacier behavior and drainage evolution. The South Tahoma Glacier possesses characteristics particularly favorable for producing these recurring floods. Over time, meltwater carves complex tunnels beneath glacier ice. Some passages become blocked by shifting ice or collapsing sediment. Water then accumulates until pressure becomes great enough to reopen the drainage system. When release finally occurs, the flood may emerge almost without warning. Field studies conducted over previous decades have documented repeated examples of this process at Mount Rainier. Scientists have observed channels abruptly changing course, glacier margins collapsing, and fresh debris deposits extending along Tahoma Creek after successive events. Fortunately, the latest debris flow appears consistent with that established pattern rather than indicating a fundamentally new hazard. Even so, every such occurrence reminds scientists why Mount Rainier demands constant monitoring. Unlike many volcanic hazards that remain confined near a summit crater, lahars possess extraordinary travel distances. Large flows can continue for tens of miles while maintaining tremendous destructive power. Historical evidence preserved within river valleys surrounding Mount Rainier demonstrates that prehistoric lahars repeatedly buried broad lowland areas now occupied by thriving communities. The volcano's most famous ancient lahar bears the name Osceola Mudflow. Approximately 5,600 years ago, a massive collapse removed a large portion of Mount Rainier's northeastern flank. That collapse transformed almost instantly into an enormous lahar that surged more than 60 miles, or nearly 100 kilometers, from the volcano. Vast quantities of volcanic debris spread across the Puget Lowland, permanently reshaping the regional landscape. Modern cities now occupy portions of those ancient deposits. Communities, including Ording, Puyallup, Sumner, Fife, and parts of Tacoma, exist within valleys repeatedly inundated by prehistoric lahars. Population growth throughout western Washington has dramatically increased potential exposure compared with thousands of years ago. That reality explains why Mount Rainier consistently appears near the top of volcanic hazard assessments conducted by federal scientists. Remarkably, the volcano does not need to erupt for another dangerous lahar to occur. Heavy rainfall, rapid snowmelt, glacier outburst floods, earthquakes, or large flank collapses could each mobilize enormous quantities of loose volcanic sediment. Even relatively small failures high on the mountain may bulk up dramatically as they descend, incorporating additional water and debris until they become far larger than their original source. Among all possible scenarios, flank collapse remains especially concerning. Volcanic edifices naturally evolve over immense spans of time. Repeated eruptions stack lava flows atop weaker volcanic ash and fragmented rock. Hot acidic fluids circulating through the volcano gradually alter strong volcanic minerals into soft clay-rich material. This process, known as hydrothermal alteration, significantly weakens portions of the mountain. Over centuries, weakened sectors become increasingly susceptible to collapse. Mount Rainier exhibits widespread evidence of hydrothermal alteration. Extensive areas near the summit contain rock transformed into relatively fragile clay minerals incapable of supporting steep slopes indefinitely. Scientists carefully monitor these weakened zones because they represent potential sources of future collapses. A large flank collapse would differ fundamentally from the relatively small debris flow detected during the latest event. Instead of beginning with water escaping beneath a glacier, millions of cubic yards of weakened volcanic rock could detach from the volcano itself. Once moving, that collapsing mass would fragment violently while mixing with glacier ice and snow. Friction would rapidly melt portions of the ice, generating tremendous volumes of water within the moving avalanche. Transformation into a lahar could occur within minutes. Rather than slowing, the newly formed slurry would accelerate through river valleys, gathering additional sediment along the way. Entire forests could be uprooted. Bridges could disappear beneath rapidly accumulating debris. River channels might become blocked before catastrophic flooding developed upstream. Although such events are infrequent, geological records prove they have happened repeatedly throughout Mount Rainier's history. One notable example occurred approximately 500 years ago when the electron mudflow traveled down the Puyallup River Valley. Evidence suggests that event may not have been associated with a major eruption, reinforcing the lesson that catastrophic lahars do not necessarily require explosive volcanic activity. For emergency planners, this distinction carries enormous significance. Residents often associate volcanic hazards exclusively with lava fountains or towering ash columns. Mount Rainier challenges that assumption. The volcano's greatest long-term threat involves rapidly moving sediment-rich floods capable of reaching populated valleys, while the summit itself appears relatively quiet. That is why extensive warning systems now surround the volcano. Networks of seismic sensors continuously detect unusual vibrations generated by debris flows and lahars. Acoustic monitoring equipment distinguishes between earthquakes, rockfalls, glacier movement, and flowing sediment. Remote cameras provide visual confirmation whenever weather permits. River gauges monitor sudden water level changes. Together, these systems provide emergency managers with precious minutes of warning should a larger event begin. Communities downstream regularly participate in evacuation drills because available warning time could prove extremely limited. Depending upon the valley involved, large lahars might reach populated areas in less than 1 hour. Schools, hospitals, businesses, and local governments have developed carefully planned evacuation routes leading toward higher ground. Signs marking lahar evacuation paths now stand throughout several communities surrounding Mount Rainier. Preparation reflects decades of scientific research rather than immediate concern about volcanic unrest. Current monitoring shows no evidence that the recent debris flow represents the beginning of an eruption. Volcanologists evaluate multiple indicators when assessing volcanic activity. They monitor earthquake frequency, ground deformation, volcanic gas emissions, thermal changes, and satellite observations. Significant unrest usually involves several of these indicators changing simultaneously. During the recent event, available evidence instead pointed toward an isolated hydrological process associated with glacier drainage. Such events occur independently of magma movement. That distinction provides reassurance while simultaneously emphasizing the volcano's complexity. Mount Rainier functions as both an active stratovolcano and a heavily glaciated mountain. Hazards arising from either system can develop separately or interact under certain circumstances. Glacier processes alone generate floods and debris flows. Volcanic processes may trigger earthquakes, heating, or eruptions. In the most dangerous situations, both systems combine to produce exceptionally destructive lahars. Climate also plays an increasingly important role. Warmer temperatures influence glacier thickness, meltwater production, and seasonal runoff. Although scientists continue studying the precise relationship between climate change and individual outburst floods, changing glacier geometry alters internal drainage pathways over time. Retreating glaciers expose fresh sediment previously protected beneath ice. Newly uncovered material becomes available for erosion during future floods. Shifting meltwater routes may create new locations where water accumulates before sudden release. These evolving conditions require continuous monitoring because glacier systems rarely remain static. Every debris flow provides valuable scientific information. Fresh deposits reveal sediment sources. Channel changes indicate erosion patterns. Seismic records improve automated detection algorithms. Drone surveys produce highly detailed maps documenting landscape evolution after each event. By comparing successive debris flows, researchers gradually build a more complete understanding of Mount Rainier's behavior. Knowledge gained from relatively small events strengthens preparedness for much larger ones. The recent debris flow also illustrates the importance of precise scientific communication. Words such as landslide, debris flow, lahar, flood, avalanche, and outburst flood often become interchangeable in public discussion, despite describing different physical processes. A glacial outburst flood refers specifically to sudden release of stored glacier water. A debris flow describes rapidly moving mixtures of water, sediment, and rock. A lahar represents a volcanic debris flow composed of volcanic material mixed with water. A landslide generally involves downslope movement of rock or soil under gravity. Although these hazards may occur together, distinguishing among them helps emergency managers evaluate risks accurately. The United States Geological Survey's classification therefore carries considerable importance. By identifying the event as a debris flow initiated by a glacial outburst flood, scientists clarified that observations matched the South Tahoma Glacier's established history rather than indicating an unexpected structural failure elsewhere on the mountain. That conclusion aligns closely with decades of previous research. Since the late 1960s, the South Tahoma Glacier has repeatedly demonstrated its capacity to generate similar events. Each occurrence reinforces the understanding that Mount Rainier's glaciers remain dynamic systems capable of producing hazardous debris flows even during periods of complete volcanic quiet. Visitors exploring the national park often encounter broad channels filled with boulders, uprooted logs, and fresh sediment. These landscapes preserve evidence of repeated debris flows extending across generations. Streams that appear peaceful during summer afternoons may occupy channels carved by vastly more energetic events. Such contrasts define Mount Rainier. Towering glaciers convey permanence, yet they constantly move, fracture, melt, and reshape themselves. Massive volcanic slopes appear solid, yet hidden hydrothermal alteration gradually weakens portions from within. Rivers flowing gently towards surrounding valleys occasionally transform into destructive torrents carrying entire forests downstream. Scientists remain vigilant precisely because these processes rarely announce themselves dramatically beforehand. Monitoring technology continues improving every year, allowing increasingly rapid detection of subtle changes. Satellite imagery now complements airborne laser mapping, drone reconnaissance, seismic analysis, and field observations. Together, these tools create one of the world's most sophisticated volcano monitoring systems. Even with such advances, nature retains the capacity to surprise. Every confirmed debris flow becomes another valuable chapter in understanding one of America's most complex volcanoes. The latest event should therefore be viewed neither with panic nor complacency. It was not an eruption. It was not evidence that Mount Rainier has entered a new period of volcanic unrest. It was not the catastrophic lahar long envisioned in emergency planning exercises. Instead, it represented another documented example of a natural process that has characterized the South Tahoma Glacier for decades, a glacial outburst flood transforming rapidly into a debris flow confined within Tahoma Creek. Yet its importance reaches far beyond its limited size. Every reminder that Mount Rainier can generate hazardous flows without erupting reinforces one of the most critical lessons in volcanic hazard science. The mountain's greatest danger often arrives not with fountains of lava or towering ash clouds, but with roaring walls of water, ice, mud, and shattered rock racing through river valleys that extend far beyond the volcano itself. For communities living in the shadow of Mount Rainier, awareness remains the strongest defense. Scientific monitoring, carefully maintained warning systems, detailed hazard maps, and practiced evacuation plans exist because history demonstrates that the volcano's glaciers and unstable flanks can become dangerous even during otherwise peaceful conditions. The confirmation issued by the United States Geological Survey on the 3rd day of July, 2026, ultimately serves as another reminder that Mount Rainier never truly sleeps. Even in the absence of erupting magma, the immense volcano continues to reshape itself through ice, water, gravity, and rock. Most of those changes pass quietly, unnoticed by the millions who admire its snow-covered summit. Occasionally, however, one of those hidden processes announces itself through the unmistakable seismic signature of another debris flow, reminding everyone that the mountain's greatest power is not always written in fire, but often in the relentless force of moving water and the immense lahars that remain its defining hazard. One question deserves careful consideration. The latest debris flow remained relatively small and behaved exactly as scientists expected from the South Tahoma Glacier's long history. Yet Mount Rainier still possesses vast glaciers, hydrothermally weakened flanks, and deep river valleys leading directly toward growing communities. Do you believe enough people understand that this volcano's greatest danger can arrive without an eruption? Or should public awareness of lahars and evacuation planning receive far greater attention? Share your thoughts, and if you found this analysis valuable, consider liking, sharing, subscribing, and tapping the notification bell so more people can better understand the remarkable and sometimes underestimated hazards surrounding Mount Rainier.